Couple quick announcements. Homework 3 was due on Friday. I mean, I know we're in the grace period. Most people still haven't turned it in, but I thought I would give everybody the warning that try to get it turned in before Friday, or we may not get it graded and returned for a while. Well, it may not happen regardless. I need to talk to Erica and Kara and see if they have time to grade this week. But the bottom line is none of us are going to be around much over spring break, and I'm going to be gone most of the following week. Oh, if you turn in your homework 3s at the last minute, they may not get graded for a couple more weeks. Just thought I'd give you fair warning. The other thing that I was going to announce, and this is, I'm not set on this idea at all. If you think this is like a horrible, terrifying idea, you're welcome to email me and say this is horrible, and I will drop the idea immediately. I should probably email this to the class, given that most people in the class are not here. But I've been toying with ways to try to make this class more relevant to the bench scientists who form the majority of the class. And I was debating about the idea of dropping the final or giving a much more abbreviated final, and in place of the final having people write like an NIH R1 or R21 application where we would be grading you primarily on your statistical analysis plan. I mean, just talking to people, I mean, this is one of the things, it's like the single biggest, most important jobs is future faculty members, but nobody ever teaches you how to do it in grad school, and I thought this could potentially be a good way to just at least learn what they're looking for and get practice doing this sort of thing. But not married to this idea at all. If you're just sitting here like, holy crap, I have no idea how to do it, I have too much to do at the end of the semester already, and I'm also aware there's undergraduates in this class, and asking them to do this could be kind of cruel, but just something I was thinking about. So, like I said, I will accept feedback on whether it's a good idea or a bad idea, and honestly, like, depending on the feedback I get, may determine the decision as much as anything. So, just something to think about, but thought I would toss that out there. Anyway, so for today, as you can see, we're discussing correlation. This is sort of an introduction to the discussions on regression, which is going to take most of the next couple weeks, because partly it's an area that I'm interested in, but partly, it's my opinion, it's one of the most useful areas of modern statistics. And there's a lot of modern regression methods that don't get taught in intro statistics courses, so I wanted to make sure to cover all that so that you're aware that it exists. But for today, we'll just start with the basics on correlation. One of the big questions that you deal with statistical methods in general is when you have two variables, like variable 1 and variable 2, and you want to see are they associated with one another. A lot of the methods we've discussed thus far are trying to answer that basic question. Regression also tries to answer that question, so I thought worth giving a general overview on this. Because oftentimes we're hoping that one variable will predict or explain the other variable, and basically, I mean, in general, the variable that you use to predict the other variable is known as a predictor variable, shockingly enough, or sometimes it'll be an input variable or an independent variable. The variable that you try to predict is known as a response variable, or also sometimes an outcome or dependent variable. And when you're looking at the association between two variables, there's usually two big questions that you want to answer. First of all, is the association real? Is it not due to chance? In which case, typically you'll do some sort of hypothesis testing to test the null hypothesis of no association. The other thing that you may want to know is how strong is the association. There are various ways to quantify that, and you usually want to use confidence intervals to quantify the strength of this association. And Next couple slides, I'm just going to do a quick review of some of the stuff we've covered already, because one thing I've learned from this class in the past is that one of the most common questions I get at the end of the semester is, okay, we've learned about 500 new statistical tests. How do I know which test to use for which problem? I know it's all somewhat confusing, but this is to try to simplify it a little bit. I'll be devoting pretty much an entire lecture to this at the end of the semester, but just to get you thinking about this now, like I said, oftentimes you have two variables. You want to see if they're associated with one another. You want to see if variable A predicts or explains variable B. And the type of test or method that you use depends a lot on what types of variables that you have. Say you have two categorical variables, and you want to see if they're associated with one another. Like, you want to say, is case status associated with pain relief? Case status is a categorical variable. You can either be in the drug group or the placebo group. Pain relief is also a categorical variable. Either you experience pain relief or you don't. Likewise, if you want to talk about the relationship between smoking and lung cancer, there are also two categorical variables. Or if you want to say, is race related to the risk of developing chronic pain after a car accident? Once again, chronic pain is categorical, yes or no. Race also has a certain number of discrete categories. So anytime you have two categorical variables, you want to know if they're related to one another, then the standard approach would be a chi-square test. You can also use some of the variants that I discussed a few weeks ago, proportion tests or Fisher's exact test, or things like that. And another common situation is if you have one quantitative variable and one categorical variable or binary variable, that say you're doing an experiment on mice in the lab, you either treat them with a growth hormone or a placebo, and for each mouse you measure their weight. You want to test the null hypothesis of no association between the treatment and the weight. Or the example we discussed a couple weeks back, wanting to know, is there an association between a baby's birth weight and smoking? That if the mother smokes, is the baby more likely to have low birth weight? In this case, smoking is a categorical variable, specifically a binary variable. It's either yes or no, whereas birth weight is continuous. Likewise, say you have two different tumor types, say you have metastatic and non-metastatic cancer. You want to test the null hypothesis. There's no association between these tumor types and gene expression. In this case, the standard approach to answering that question would be a t-test, where you compare the null hypothesis that the means of the two groups is the same, or you could use bootstrapping or other non-parametric approaches. And today, and for the next couple weeks, we'll be considering the next possible set of associations between two variables where you have two quantitative variables. That, say, you have data on people's ages and their pulse rates. You want to test the null hypothesis the pulse rate remains the constant as people get older. Or say we take the cancer example again, that you have a bunch of tumor samples from a set of cancer patients, and you have the time until the cancer metastasizes. You also have gene expression data. You want to see if some genes are associated with a quicker time to metastasis. Or say you want to test the null hypothesis of no association between alcohol consumption and HDL level or bad cholesterol. That's kind of a famous example because of its non-linear, like U-shaped association, that if you drink no alcohol whatsoever or lots of alcohol, then you tend to have higher HDL levels than if you drink a modest amount of alcohol. So we'll be spending plenty of time over the next couple of weeks discussing formal methods and tests for testing the null hypothesis of no association between two quantitative variables. I'm sure a couple of weeks from now you'll be really sick of this and never want to hear about it again. For the time being, we'll just focus on describing the relationship between two variables. The standard way, if you have two quantitative variables and you want to try to visualize the association between the two variables, you can generate what's known as a scatter plot. Probably most of you have seen this before, but basically you just take the value of one variable, put it on the x-axis, the value of the other variable, put it on the y-axis, draw the dots. This is a data set that's built into R. I believe it's called CARS, where basically the x-axis, this is old data. Car brakes work a bit better than this nowadays. But basically the x-axis is the speed that a car is going when you slam on the brakes. The y-axis is how far the car traveled before it came to a complete stop. I want to test the null hypothesis of no association between speed and stopping distance. By convention, when you draw the scatter plot, the x-axis is the predictor variable, the variable that you think will explain the other variable, and the y-axis is the response variable. In this case, we think speed is going to explain stopping distance, so speed goes on the x-axis. The R commands to do this is called plot. As I said, this data set is built into R, so you don't need to load it. All you type is attach cars. And then cars is a data frame with two columns, one called speed, which is the speed of the cars, and distance is the stopping distance. So you go plot speed, comma, dist, and then you can give it an X label and a Y label and a header, just like with other plotting commands in R. So, now that I remember, this is data set is from the 1920s, so yeah, that's why the brakes seem to work so badly. And in general, if you just say plot x comma y, that'll plot a scatter plot of y versus x. And if you use the plot function, you can, in fact you should, specify the parameters xlab, ylab, and main to label the graph, as we did in all our other previous R functions. In the real world, if you try to submit a paper and your graphs aren't labeled, there's a good probability that you'll have reviewers yelling at you. So, couple comments on scatter plots. As I said before, by convention, the predictor variable should go on the x-axis. I mean, it doesn't matter that much, but everybody does it that way, so you probably should too. And as I'll show you here in a minute, the appearance of the scatter plot can depend on the scale that you choose for the x-axis and the y-axis. Generally speaking, I never mess with this because generally speaking, R does a pretty good job of choosing the scale by itself, but there are commands that you can do if you need to override it. I won't go into those, but if you're ever using R for a figure in a paper or something like that and you need to override the defaults, you're welcome to shoot me an email and I'll help you with that. And the other thing to keep in mind in terms of like making your plot readable, obviously you want to label it, but you can do various things when you do these plots, just like changing the fonts, changing the size of the labels, the size of the plotting characters, the colors, everything else. There's ways to do all of this in R. I mean, I could easily devote an entire lecture to the plotting commands in R. I won't make you do that because the whole thing's kind of confusing. It's a lot of weird parameters to remember. I usually have to look it up myself. But R can do lots of fancy things with the graph. If you're plotting like two different variables on one graph, you can plot one variable in one color, one variable in the other color, all sorts of fun things like that. And these couple slides are intended to illustrate why it's important to do a good job of choosing your x-axes and y-axes. This graph shows the death rates from coronary heart disease over a period of about 7 years, and just shows a y-axis going from 0 to 600 deaths per 100,000. If you plot a graph like this, it's not changing. It's remaining exactly the same from year over year. Well, is that really true, or did we just choose a lousy job of coming up with a scale on the y-axis? Because if we plot it like this, then suddenly it's looking quite a bit better that the death rate does seem to be decreasing over time. This kind of illustrates the point that when you choose the scale, particularly on your y-axis, you want to choose the scale to give you as much to visualize the data as easily as possible. In general, at least when you're using R, it usually does a very good job of choosing the scale automatically. I almost never need to mess with it, and for the purpose of this class, if you simply use R to choose it for you, you should be fine in pretty much all cases. And things to look for in the scatter plot is just like, first of all, overall pattern. Is the relationship between x and y more or less linear? Do you see like a curved relationship? See gaps, clusters, things like that? Do you see data points that don't fit the general pattern, other outliers like that? Is there a strong association, weak association, all these sorts of things? And my personal opinion is that in general, when you're doing these regression types of problems, it's always a good idea to draw scatter plots of the predictor variable versus, or the response variable versus the predictor variable. If there's multiple predictor variables, plot it versus each one, just so you can sort of visualize, okay, is there a relationship between the two? Are there any data points that don't fit the pattern? We'll be discussing all this in more detail over the next couple weeks, but just to get you thinking about all this. Just some terminology. When you talk about positive and negative association between two variables, you're probably familiar with this terminology already, but in case you're not, positive association means that when variable 1 increases, the second variable also increases, and negative association means that as one variable increases, the other variable decreases. This is, like I say, straightforward enough, and it's sufficient to describe the relationships between the vast majority of variables. Other possibilities exist. There could be no association whatsoever, or you could have a nonlinear association. Typically, it would be some type of U-shaped association. That's not common, but it does happen, as I'll show you here in a second. So, this slide shows examples of linear associations or lack of linear associations. Upper left-hand corner, there's no relation whatsoever between x and y. It's just noise. Number 2 here, there's a positive linear association. See that the value of y tends to increase as the value of x increases. Graph 3 here is strong positive association. You see it's very close to a straight line. Graph 4 here shows some evidence of a negative linear association, but it's very weak. It's unclear whether or not it's due to chance. Graph 5, that's a better linear association. You see it starts to look closer to a straight line. Graph 6 is a ridiculously strong negative linear association. In practice, you'll almost certainly never see anything that strong unless it's simulated data or something, but that's what it would look like. And to define the relationship or quantify the linear relationship between two variables, you can use this quantity called correlation, which is calculated as follows. I'm never going to ask you to calculate this by hand because it's a major headache. There's a simple R command that will do the same thing, but if you ever need the formula for some horrible reason, there it is. But for this class, you can probably ignore that formula and never use it again. Anyway, properties of the correlation coefficient, it's always between -1 and 1. If the correlation is 1, that implies a perfect positive linear association. That is, that if one variable is x, the other variable is y, then if r is equal to 1, then that implies you can find a and b such that y is exactly equal to a plus bx, where b is greater than 0. Like, the standard example of that is if you're converting between Fahrenheit and Celsius, the correlation coefficient would be 1 because there's a linear function that perfectly captures the relationship between the two variables. If r equals -1, that would be a perfect negative linear association. You would have y equals a plus bx, where b is less than 0. That basically it will be a line with negative slope that perfectly describes the relationship between the two variables. If r is exactly equal to 0, that indicates that there's no linear association between the two variables. They can still be associated in a nonlinear manner, and in practice, if you calculate the correlation between two data sets, unless you specifically design them to be uncorrelated, you'll almost always have some non-zero correlation. But if the correlation coefficient is close to 0, that implies that there's no association between the two variables. And here, in a minute, I'll describe how you can calculate confidence intervals for correlations if you need to test the null hypothesis the correlation's actually equal to 0. So, going back to the illustration from a few slides back, recall graph 1 where there was no correlation between the two variables. The correlation in this case was 0. For a semi-strong positive association, here we have a correlation of 0.5. For the very strong positive association, there we get a correlation of 0.9. The weak negative association here was -0.3. The correlation's negative now because y decreases as x increases. For graph 5, the stronger negative correlation, that's -0.7. For the ridiculously strong negative correlation, it's -0.99. As you can see, it's almost a straight line in that case. If it were a straight line, the correlation would be 1 or -1. Oh, the correlation of the direction doesn't matter when you calculate correlation. The correlation of x with y is the same as the correlation of y with x. The correlation has no units. If you go through the formula for the correlation, you'll see that you end up dividing the units by themselves and they end up canceling out. Oh, it's between -1 and 1. It's not like -1 inches or anything like that. It's a unitless measure. And just in case I haven't beat this particular horse enough for the course of this class, the correlation says nothing about causation. If you can find two variables that have a perfect positive correlation, that where one variable does not cause the other variable, that I'm trying to think of some silly example of that. I mean, well, I guess you could just think back to the very first lecture in this class where we showed, for instance, a very strong positive correlation between the number of Facebook users and the interest rates on Greek debt. Does that imply as more people sign up for Facebook, Greece's credit rating gets worse? Or does it just kind of indicate they're both correlated with time or something like that? So high correlation does not imply causation. Hopefully I've made that point enough times by now, but I'm going to make it again because it's important. And another thing to keep in mind is that the correlation coefficient measures only a linear relationship. Just because a correlation coefficient is not significantly different from 0 does not imply that no association exists between the two variables. This graph here shows two variables that are completely uncorrelated, but still strongly associated with one another just because the relationship is nonlinear. Oh, this type of situation is unusual, but it does happen, so it's a bit dangerous to say there's no relationship between x and y just because the correlation isn't significantly different from 0. Anytime where you have like some sort of U-shaped association, like I said, alcohol consumption in HDL is a classic example of that, then relying just on correlation can give you misleading results. And other properties of the correlation: it's not robust, that is, it's not resistant to outliers. You can have a bunch of variables, you can have a bunch of data points that are basically not associated with one another, and then like an extremely large x associated with an extremely large y. That can by itself can give you a positive correlation even if the rest of the data points are not associated. That illustrates once again why it's a good idea to always plot the graphs to see if an outlier or a small set of outliers is driving your association. And the correlation is not the same thing as the slope. There is a relationship between the two that I think I'll show that in another lecture, but there's not a simple relationship between, there is a one-to-one relationship between correlation and slope, but they're not identical. And just to illustrate the fact that the correlation coefficient doesn't tell you everything about the association between two data points, here's 6 different graphs, all of which have a correlation of 0.7. If you're looking for a linear relationship, the graph in the upper left-hand corner is the type of thing that you hope to see. There, you see basically a linear association between x and y, where y equals x, some linear function of x plus noise, easy enough. But you can also create other situations with equal correlation where the relationship is very different. Example 2, there's a perfect linear association except for one outlier. If you remove that outlier, the correlation would be 1, but with the outlier you end up with a correlation of 0.7. This graph, you have a nonlinear association, a U-type association. It still gives you a positive correlation, but in a nonlinear pattern. Then example 4 indicates that where you really have 2 clusters of points, one higher than the other, but without a linear association between the two. Example 5, you really have 2 different, looks like you probably have 2 different subsets of variables with 2 different slopes. Sometimes you'll see patterns like this if like you're looking at like height over time for both males and females. For instance, you'll end up with a graph of males that looks like this and a graph of females that looks like this or something like that, in which case you wouldn't want to model it as a linear association because there's a confounding variable there. Then you also could have a pattern like this, sort of fan shape, where modeling it as linear would be dangerous because your error would be higher for higher values of x. This just illustrates the point once again why it's a good idea to plot the data and not just mindlessly calculate the correlation coefficients and think that it tells you everything about the association between x and y. Yeah, because I basically just said that. Same, you can have data sets with the same correlation that look different, so graph the data. And a quick note on terminology: if you really want to be a purist, the term correlation should only be applied to quantitative variables. So if you say something like there's a correlation between ethnicity and obesity rates, that's technically not correct, because ethnicity is not a quantitative variable. In this case, it would be better to use a term like association rather than correlation. Now, personally, I always get annoyed when people get really uptight about terminology like that. So, I'm not going to be an ogre about this in this class, but if you've spent enough time in academic life, you may have learned that there are some people who's just like have this strong need to feel like they're smarter than everybody else, and these people tend to review your paper sometime, and if you use the word correlation, a place where they think that you're not supposed to use correlation, they'll think that you're stupid and tear your whole paper to pieces. Stupid, yes, but welcome to academic life, so it's better to try to just err on the side of using your terminology as correctly as possible so that you avoid the wrath of reviewers when you're trying to publish your paper. And as I said earlier, correlation does not imply causation. Confounding variables can mess things up. Two of my favorite examples that I think I've used already in this class, but I'll bring them up again because I like them, that shoe size and test scores is a famous example of this, where the size of children's shoes is strongly correlated with their scores on tests. That doesn't mean that big feet imply bigger brains, except indirectly, in that if you're older, both your feet and your brain tend to be larger. Or another famous example was when they first developed these regression methods during World War II, and they found that for bombing runs, the more enemy fighters that were in the air trying to shoot down the bombers, the more likely the bombing run was to succeed. They couldn't figure that out for the longest time until they realized that both of these variables were associated with cloud cover, that on a cloudy day there's less enemy fighters attacking you because they can't see the bombers in the air, but the bombers can't see the target either, so they're less likely to hit their target. And the other thing to keep in mind is if you look at large numbers of tests, you can find spurious associations. That a famous example of this is over a course of about 50 years, the winner of every single presidential election could be predicted by the outcome of the Washington Redskins' last home game the week before the election. That for like this 50-year period, if the Washington Redskins won their final home game before the election, then the incumbent party stayed in power. If they lost their final home game, then the incumbent party got kicked out of power. I think this continued until 2004, where the Redskins lost their final home game, but George Bush won the election anyway. is there really any sort of association whatsoever between the Washington Redskins and the presidential election? I very highly doubt. I think this has much more to do with bored people looking around at crazy variables and saying, oh my gosh, look at this association between the Redskins and the presidential election. So if you look at a bunch of different variables, you can find spurious associations. So don't assume that there's a real relationship between X and Y just because they happen to be positively correlated. So now that I've said all this, how do you calculate correlations in R? Well, it's actually quite easy. There's this variable called cor. For the car's data set, I find the correlation between the speed and the stopping distance. The correlation is about 0.81 in this case. Consistent with what we saw in the scatter plot, that it looks like there's a fairly strong linear association between the two variables. And in general, cor x comma y computes the correlation between x and y. When you use this command, make sure that the elements of x and y are aligned correctly, that each row of x corresponds to the analogous row of y. If you just import data from a spreadsheet or something, you'll probably have that set up automatically, but it's a good thing to pay attention to, because if you get shifted by one, your correlation will be completely off. And let's say that we want to make inferences about the correlation coefficient. Say you want to calculate a confidence interval for the correlation coefficient or test the null hypothesis that the correlation is 0. Testing the hypothesis is actually easy. It's difficult to compute the distribution of the correlation coefficient exactly. There are ways to test the null hypothesis, the correlation 0. We'll discuss this in an upcoming lecture, I think on Wednesday's lecture actually. And if you want to calculate a confidence interval for the correlation coefficient, you can use bootstrapping. And I'm just going to include this as an example, partly because this lecture wasn't filling enough time otherwise, partly because, there have been a number of cases in real life where I needed to calculate a confidence interval for a correlation. My collaborators thought it was impossible, and they were kind of excited when I showed how you could do this using bootstrapping. So if you ever need to do this, here's some R code that you can copy for that. Say that we want to test the null hypothesis. There's no relationship between speed and the stopping distance for the car's data set in R, so we try to compute a 95% confidence interval for this correlation using bootstrapping. How do you do it? Well, I'll show you. First of all, you have to define the bootstrap function. I define this function cor.boot. Define it similarly to other bootstrap functions. First step is I say x.star equals xi in bracket x bracket I comma. As you'll recall, in general when we use bootstrapping, we're selecting some subset of the data. In this case, we want to select some subset of the rows of the data, that we're assuming that the variable x has 2 columns and any number of rows. We want to resample from the rows with replacement, so that's why I say I comma. That says select some subset of the rows, and select for that subset of the rows, select both columns. So we're just basically resampling from the rows with replacement. Once we do that, then we take the correlation of the first column and the correlation of the second column. If you didn't follow all that, don't worry about it too much. As I said, for the purposes of this class, if I ask you to do this at all, you can basically just copy what's on this slide. And as I said, I think we've talked about this before, but just as a review, if X is a matrix or a data frame in R, if you say X1 comma, that gives you the first row of X. X comma 1 gives you the first column. X1 colon 5 comma gives you the first 5 rows. So when you say Xi comma, that tells R resample from the rows with replacement, return a data set containing those rows after you've resampled with replacement. And then you can calculate the Bootstrap confidence interval. First of all, you load the boot library, then you say cars.boot equals boot. And then the x variable, I just say cbind, speed, and distance. In other words, I give it a matrix with two columns, one of which is the speed, the other is the distance. Basically, we just want to find the correlation of one column with the other column. The Bootstrap function core.boot, say I want to do 1,000 Bootstrap replicates. And then I use boot.ci to calculate the 95% Bootstrap confidence interval for the correlation in this case. And as an aside, this is what here you see what I talked about in the lecture on bootstrapping. You see this warning message here. It says some BCA confidence intervals may be unstable. If you get that message, you generally want to avoid using the BCA intervals. Usually, in that case, I just use the percentile intervals because they tend to be the most reliable after BCA. I mean, you can see, even when it says they're unreliable, there's not much difference between percentile and BCA, but I usually use percentile rather than BCA in those cases. That if you really want the best confidence interval possible and you get the warning that the BCA intervals are unstable, then sometimes if you increase the number of Bootstrap replicates to 10,000 rather than 1,000 or something like that, you'll get stable Bootstrap BCA intervals. But yeah, I've probably already given you way more details than I should ever give about bootstrapping in an introductory course. For purpose of this class, if you see some BCA intervals are unstable, just report the percentile intervals and we'll be happy. And in general, as I said, cbind x comma y will combine x and y to create a matrix where x is the first column and y is the second column. rbind is similar, but you'll end up with a matrix with two rows and however many columns. It'll bind rows rather than columns, for instance. So, things to remember for today: correlations, the strength of the linear association between two quantitative variables, and the overall pattern is more important than the correlation, that plotting the variable is always more informative than just listing the value of the correlation. It's possible to have a strong association but a low correlation. And correlation does not imply causation, just in case I haven't beat that horse enough already. And here's the new R commands for today: plot, core, and cbind. Any questions about anything today? If you're still trying to get homework 3 done, you're struggling with it, please email me. We really try not to torture people too much with these homework assignments. I'm happy to set up a time to meet, talk on Skype, phone, whatever the case may be.